Hello everyone, good evening, welcome back. I have a slightly unfortunate announcement, or sort of weird announcement. I'm looking around the room, I see a lot of familiar faces, that's good. However, on Sunday night in Toronto we had this shooting. I live about 3 blocks away from where it happened, and if I decided to walk home, I would have been shot. So there's a little bit of a tension in Toronto. If you live in the East End and you're feeling kind of weird about the whole situation, I'm really happy to talk to you about it and this kind of thing. I'm happy that I see a lot of familiar faces. You know, no one's missing or was shot. That's great. But if you're feeling tense about it and you live in the East End, just let me know. I'm happy to talk about it. With that weird note out of the way, I want to point out some stuff that happened on the blog. I got a bunch of emails about question 4 off of homework 5. So if you're not sure how to interpret the phrasing of the question, I put up some diagrams to sort of illustrate what was going on there. We've got this sphere of big radius r. Okay, so the red sphere is supposed to be big radius r, and the region that it cuts out is supposed to have height h. Okay, so we're supposed to go from here to here and have height h. Okay, and if we took that picture and tilted it forwards, we'd see through the hole in the sphere. Okay, we'd see through and see into that hole. So that's supposed to be what that question was illustrating. I hope that that's helpful for people. Were there any other questions about homework question 4? Question 4. Okay, so I hope that diagram helps. We've got our last, one sec. This is no good. One sec. Okay, homework 6 is supposed to have a link to it right here. Unfortunately, there's no link. There'll be one after lecture. If you're really like, I need homework 6 right now, which a lot of people are, that's a reasonable response. Please go to pg80.ca/teaching. Okay, and then select our course B41, and homework 6 is right here. There'll be a link to it after lecture today. This is the last homework assignment, so that's excellent. We're done. We're there. This is the last homework assignment. And I thought it would be helpful to make it half a review of the course. Okay, so I took half the questions from old homework and I changed the numbers and changed them conceptually a little bit. So the first 5 questions are sort of review type questions, not related to what we're currently doing, but just to stretch the old muscles. Okay. And then the last 5 questions are related to material from this week. Okay, so the last 5 are about this week, and the first 5 are to just get you playing with old ideas. Okay, so right. So the link is not there. It'll be posted after lecture. Very good. And then our last announcement is we're going to have a mock final this coming Friday. So this will be a good time. You'll get to see what the thing looks like before you write it. I got the feedback from a lot of people that there was too much weight put on the multiple choice for the midterm. Yeah, some people are like, I hate multiple choice. Okay, so I put less weight on them. Now they're worth 2 marks each. And they make up less of a percentage of the exam, and that percentage is going to be in short answer questions and long answer questions. Okay, so if you hate multiple choice, that's reasonable. There's less multiple choice. You'll see this on the mock final. So if you want to come out and write that, please do. It'll also be available on the blog for people who aren't able to come out and write it. We're going to go from 12 till 3, and I encourage you to stay for the whole time. I'm going to collect the test papers after the time, and I'm going to take out all the hard questions from the final exam, okay? No hard questions, okay? So I really want to see what you guys answer so that I can make it something that will be easy to pass the real final, okay? Any questions or thoughts there? Questions, thoughts? So, please bring a snack. Please come out and try and write for the full 3 hours just to see, what it will be like to write the final exam. Okay, so that's all the news. Good. Okay. Excellent. Okay, so what are we up to today? Okay, so today we're going to focus on the thing that we talked about at the end of Thursday, this thing Fubini's theorem. Okay, so changing order of integration, that's section 5.4. Okay, and it's all powered by this one theorem, which says this. Okay, if we have these guys in order dx, dy, we can switch them. And if the region is nice enough and the function is nice enough, those integrals should be equal. Okay, so this is Fubini's theorem. But actually switching that order is sometimes quite technical. So I want to get into the technicalities of how to do that switch. Okay, write down both orders of integration for f of xy on the triangle bounded by these guys here. Okay, so we're going to start off by writing down one integral in two ways, and that'll get us in the mindset of switching things. Okay, so we always start off drawing the diagram. Okay, so we've got 2 on the y-axis. Four on the x-axis, and then 0, 0 there. Okay, And now we have to give a name to this line here. So our line will be y equals 2 minus, or sorry, negative a quarter x plus 2. Okay, so if we put in x equals 0, we get 2. If we put in x equals 4, we don't get that. Sorry. That should be slope negative a half. Okay, so now we've got a name for that line. So let's write down the integral in both ways. Okay, so we'll do the order dx dy first. Okay, so when I set these things up, I like to work from the outermost integral inwards. So I set up a big box, and then I figure out what should go in that box. Okay, so my bounds in the y direction will be from 0 to 2. Okay, so I'm going to integrate y from 0 to 2. And then I need to figure out where x goes. Okay, so if I start at 0, what x do I get to is the question. And to do that, I need to figure out x in terms of y. So I rearrange this equation, and I get that's equivalent to y minus 2 is negative a half x. Okay, doing the algebra I get there. Okay, so if I'm going to move along from 0 to the end of this triangle, I need to figure out what that x coordinate is. So I get that it's this guy here, and I get 0 to negative 2y plus 4. Okay, so I encourage you to write the outermost bounds first, and then work out the details for the inner bounds. Are there questions there or thoughts about why we had to solve for x, maybe? No? Everyone's doing okay? Sweet. You can fit it in. Okay, so now let's go in the opposite order. Okay, so in the opposite order, we start off with our bounds for x. So x will run from 0 to 4. And now we put in our bounds for y. And at each slice, y is going to start at 0 and move upwards until it hits the bounding curve. Okay, so it moves upwards, and we get to this. Okay, the boxes are there just to illustrate the order in which we do things, but I'll make a little note here. Okay, work from the outside bound inwards towards the center of the thing. Okay. So I've been making a big deal out of changing order of integration, but I haven't especially said why we would ever do this. So I want to illustrate with a bit of an example. Okay, so take a couple moments and try this out on your own. Assume that this question is on the exam and you're trying it right now. Okay, take a couple moments, write it down, see what progress you can make with it. Sorry, this guy here should be y divided by 2. How's it going here? Yeah? Okay. Do you spot a difficulty with this? You're good? You're good? Okay. You should zoom in, otherwise you'll go blind. Okay, let's bring it back, folks. Okay, so is there a place where people are stuck with this? Yeah? Hard crowd tonight. Okay, so interesting fact. I find this just kind of like tantalizing. So this guy was an equation that was studied by like Euler and Lagrange and all these guys. And they found that it was very, very, very hard to get an antiderivative for it. So the usual way of getting the antiderivative for this guy is to do something like this. And then integrate it term by term. It turns out there is no simple formula for this antiderivative. So there is no or I guess I should say there is no simple antiderivative here. So this is one of the weird things about integration is we write this formula down, it looks like something that should have a nice antiderivative, and it turns out there's no simple antiderivative. Okay? And if you're very mathy, this is a subject called differential Galois theory. It's very beautiful. But it can prove results like there's no simple formula. Okay, so we're stuck at the first step here. When we try and do this, there's no antiderivative. Okay, so because this example is part of the lecture on changing order of integration, we change order of integration. Okay, so let's do that. So when we change order, it's always helpful to sketch the region that we're integrating over. Okay, so we're going to work from the outside again. We're going to focus on where dy goes. So it says we go from y equals 0 to y equals 4. Okay, and then that x gets integrated from y over 2 to 2. So that will be x goes from, here's x equals 2. And now we're going to go from y over 2. So that will be here. Okay, for help with graphing this, I often find it helpful to turn my head sideways and switch the axes by turning my head. Okay, so the region that we care about integrating over is here. Okay, and now we'll switch the order of integration and see what happens. Okay, so we want to say that this guy is hard to deal with, but let's deal with the integral with the order reversed now. Okay, so with the order reversed, we're integrating from 0 to 2 in x. So we're going this way. And then inside that, we're going to be integrating, we have to work with this equation and get it in terms of y now. Okay, y equals 2x. Okay, so we're going to be integrating from 0 to 2x. Okay, and our integral will stay the same. And now we're doing this guy here. Questions or thoughts about how those coordinates got switched? You guys are pros. Awesome. Okay. So now we're taking the antiderivative of this in terms of y. So we notice that everything in here is constant with respect to y. So we get y e x squared from 0 to 2x dx. Okay, and then applying fundamental theorem of calculus with our bounds, we get this. All this stuff goes away. And now we're left looking at that. Okay? And here, our single variable techniques do apply. Right? We can say, this is a nice integral if I take u is equal to x squared. I get du is 2x dx. I've got a 2x dx, so I can name this whole guy the following thing, and I get e to the 4 minus e to the 0. Okay, so when we change the order of integration, we can sometimes get something that's easier to integrate. Questions there? Thoughts? Right, so the first thing that we had, there was no simple antiderivative. When we changed the order of integration, we got something that we could antidifferentiate. Okay, I'd like to do another example in a very similar spirit. Okay, so now here we've got a cubing function. Again, it's hard to find an antiderivative for this. The only antiderivative we can get for e to the x cubed is a power series. So hard to get an antiderivative here. Okay, now what we're going to do is we're going to switch order of integration. Oh, sorry. We'll start off by drawing the thing. Okay. This is also to get a little bit of practice in drawing the shapes of these regions. Okay, so start off with y, right? We start off with our outermost bound. It runs from 0 to 1. Okay. Then x is going to run from root y to 1. Okay, so it's tricky to figure out what this curve looks like, this x equals root y. Well, it'll start here. And as x gets bigger, it's going to go up to 1 eventually. Right? But how does it go up to 1 is the question. So, right, so we put in some numbers. You know, we could put in y equals, say, a quarter. If we put in a quarter, we take its square root, we get a half. Okay, if we put in a half, we get 1 over root 2. Okay, and we see that this guy should be going up sort of like this. X is equal to root y. And we can check our work by squaring both sides. Okay, when we square both sides, we see that it should be concave up like that. So that's good. That's the region we care about. So when we switch the order, now we'll get dx on the outside. X will run from 0 to 1. Y will run from 0 to x squared. Oops. Okay, now we're left looking at this integral here. Okay, so when we integrate it, we get here. All right, and now this is the kind of thing we can approach with single variable techniques. So I'll leave that there, and we can approach single variable techniques. Okay, very good. Okay, there's one topic that is sort of very, very tangential to this that I want to bring up because it comes up in the homework. Okay, and this is the so-called min-max inequality, which is a way of bounding functions based on their mins and maxes. Okay, any function on a compact closed set achieves a minimum. Oops. Achieves a minimum little m and a maximum big M. Okay, so this is our extreme value theorem, which is extremely valuable. So I should say that. Okay, and I want to make this into a sort of a quantitative thing, something that we can use for estimating values. So this gives us an inequality which says okay, let the area of S be A of S, then we get the following statement about the value of the integral, that it's going to be somewhere between the minimum times the area and the maximum times the area. Okay? I just want to state what this would look like in one variable, because in one variable the pictures are much easier to draw. Okay, so for one variable, we'd have the following statement. Okay, so if we had a function like this that we knew was continuous, we could bound its value by the minimum times the length and the maximum times the length. What would that look like graphically? We'd have some curve here. Like this. And the minimum of this curve would happen here. Okay, so the area of that box would be m times b minus a. And if we had the max here, then the area of this box would be m of b minus a. And somewhere the area under the curve is going to lie between these two boxes. Okay, so it's going to be fit somewhere in the middle there. Between these two guys. Okay, and we can imagine a similar argument working in multiple dimensions now. Okay, so if we had some kind of function over a disk. We could imagine the disk sitting below it and the thing above it, and the volume will be somewhere between those two estimates. Okay, so I want to show where this gets applied in homework questions. Okay, so the thing that we have to integrate is very complicated. It's not clear how to integrate e to the sine, and I think that any kind of tricks that we play are going to be a little bit difficult here. We'll just let these folks leave. Goodbye, friends. Good luck. Safe journeys. Okay, sweet. So we're here. We've got these two bounds. How on earth do we get these bounds? So the first step is to estimate the value of the function. Okay, so we're going to estimate the value of the function. And what do we get there? Well, we get that sine is always between -1 and 1. So no matter what I put in for theta, I'm always going to have that bound on sine. So what that'll tell me is that if I take exponentials of all this stuff, I get that e to the sine theta is always going to be sandwiched between e to the -1 and e. Okay, so my values will always be sandwiched between those two. And now we calculate the area of the region in question. Okay, here it's a square. The bounds on each integrand are the same. Okay, so to calculate the dimensions of that square, we use height times width. Okay, and that gives us 2 pi times 2 pi. Very good, so we get 2 pi times 2 pi. And we get 4 pi squared. Okay, so that's where this number comes from, the 4 pi squared. And this comes immediately out of the min-max inequality. Okay, so we apply the min-max inequality. We get here little m times area and big M times area. Okay, so we know that the value, whatever this crazy thing is, it's pinched between these two numbers here. Okay, there's one last topic I want to touch on just very briefly. I think you guys probably will get it quickly, have a handle on it. I want to touch on the topic of triple integrals, and then we'll come back to that on Thursday morning. Okay, so triple integrals are exactly like double integrals, but more. I guess, yeah, there's no better way to say it. Okay, so what do we do with the triple integral? This is something like this. So the dv usually represents volume. Okay, and we integrate 3 times. Okay. Find the volume of a box of height h. Width w and length l. So if you say what you learned in school today, you can say you learned the volume of a box. Okay, so how do we calculate this with fancy triple integrals and stuff? Right, so we're going to put our coordinates on here. X, y, z. We're going to call this the width, length, and height. And then the volume will represent the following way. So we'll say, we'll go in dz first. Okay, so z is going to go from 0 to h. Then we'll go in the y direction. It'll go from 0 to w. And then in the x direction, we'll go from 0 to l. Oh, I should have written them down. Okay, and to get volume, we're just going to integrate the function 1. Okay, so let's see how that would work. Aha. Okay, so calculating out the volume. Right, we take the antiderivative of 1 in the direction x. Okay, when we apply fundamental theorem, this will evaluate to L. Right, so it's L minus 0, so we just write L. Now we take the antiderivative in the direction y, so we get a y there. And now we take the antiderivative in the z direction. And we get the formula we were expecting, length times width times height. Okay, so triple integrals, very much the same thing as double. We're going to do one more. We'll pick this theme up on Thursday. Yes, very good. And I'm going to post the homework like immediately. I don't know why it didn't go on right now. So. Be there in a moment.